All right, today we're going to talk about eigenbases and diagonalization. So last time we introduced the concept of an eigenvector. So remember that an eigenvector is a vector v where AV equals lambda v, and this lambda is the eigenvalue. And just for emphasis, every time you hear eigenvector, this is the equation that should pop in your mind. So this is the essence of what an eigenvector is. So every time you want to check something's an eigenvector, you use this equation. Every time you want to use an eigenvector as in a bigger context, you use this equation, right? One major consequence of this is diagonalization, which says that in many cases, but not all cases, we can write A as SDS inverse. Now, this is one major consequence of eigenvectors, but it is not the essence of an eigenvector. So don't jump to this every time you're asked to do something with an eigenvector. This is just one big thing you can do with it, but not the main thing. The main essence is this one. So this is what you should think about every time you get to an eigenvector. Last time, I kind of told you without proof that this SDS inverse is made up of S is going to be the matrix of eigenvectors, and this D is the matrix, the diagonal matrix encoding the eigenvalues. And there's no necessary reason why this has to be the case. I just kind of told this to you. So what we're going to spend time today doing is focusing on proving this fact that if you can diagonalize a matrix, then it has to be in exactly this form. And there's also a converse to this as well. If you have enough eigenvectors and eigenvalues, then of course you can diagonalize it. All right, so this, what we're going to do today, the fun fact we're going to focus on today, is that if you have a bunch of vectors, v1 through vn, that are eigenvectors that form a basis of Rn, then let's actually write this. So if you have this, then you have A is diagonalizable. And vice versa. So this says if you can diagonalize A, then that diagonalization must encode the eigenvectors and eigenvalues. And if you have eigenvectors and eigenvalues, then you can diagonalize A. So this goes both ways. So this effectively says the only way you can diagonalize it is with eigenvectors and eigenvalues. Okay, so let's go ahead and see why this is the case. But before we continue, I just want to mention that this has a special name. This is often called an eigenbasis. So if you have a bunch of eigenvectors with different eigenvalues, so this is not necessarily the same eigenvalues, then we're going to call that an eigenbasis. So one way of saying this fun fact in a much more compact form is that A has an eigenbasis if and only if A is diagonalizable. So you can get a basis by diagonalizing it, and you can diagonalize a matrix using the eigenbasis. All right, so let's go ahead and prove this fun fact. We're going to use a lot of the things that we've learned throughout linear algebra to do this. So the proof here, we need to go both ways. So we need to suppose that we have an eigenbasis. It has eigenvectors v1 through vn that form a basis of Rn. And we want to show, our goal here is to show A can be diagonalized. All right, so let's just start with it. So what we're going to do is we have these vectors. So we have the vectors v1 through vn. What we're going to do is we're going to just call S this matrix. So S is equal to this matrix. Now, we want to show that this, in fact, is diagonalizable. So we don't actually know that there's a diagonal here. And we're just going to let D be equal to the corresponding eigenvectors. And now what we want to do is, now our new goal is to show that A is equal to SDS inverse. As a minor note, since this forms a basis, we know that S is invertible. So that's an important thing. So we know we can actually use S inverse, and now we just need to show that A is equal to SDS inverse. All right, so how are we going to do that? So the first thing we're going to do is show that, in fact, A works in exactly this thing. So we want to show that SDS inverse times VI is equal to what we want, is equal to AVI. So we're going to show that these matrices coincide on any eigenvector. All right, and this is enough because there's another fun fact that we have. And this is an important fun fact that's kind of under the rug of everything that we've been doing, is that if, maybe a better way of putting it is not if, is that a matrix is uniquely defined by how it transforms a basis. Right, so if you tell me exactly what a matrix does for a basis, generally it's the standard basis, right? You tell me what happens to 1, 0, and you tell me what happens to 0, 1. That's going to uniquely define the matrix. There's nothing really special about 1, 0, and 0, 1. You can give me what happens on any basis, and that's going to uniquely define the matrix. And so here, if we can show that what happens to SDS inverse and what happens with A is always going to be the same on the eigenbasis, well, that's a basis. So therefore, those matrices have to be the same. All right, so what we're going to do is we're going to just compute this. Now, we know that if we get this to work, then we're done. And we know that on the right, this is equal to lambda I times VI because there's a corresponding eigenvalue. Eigenvalue for VI. So what we want to do, our new goal, right? So we started with this goal of showing that these matrices are equal. We're going to do that by showing that they're equal on a basis. And now we know that AVI is equal to lambda I VI, right? And so our new goal is just to show that SDS inverse times VI is in fact equal to lambda VI. That's our new goal. So if we do that, then we've shown that these matrices have to be equal. All right, so let's do that. All right, so we're going to take this right here, SDS inverse times VI. And now we can expand this. So remember, S is just the matrix of eigenvectors. Our D is proposed to be this diagonal matrix. And our S inverse It's just S inverse times V. And we're going to evaluate this and see if we get, in fact, lambda I times VI. All right, so we're just going to do this right to left. And the first step is applying S inverse times VI. All right, so this is where we're going to use what the inverse really means. Right? Normally, the inverse, we think of it as what it undoes a matrix, but it also does something else. So the matrix, the inverse matrix answers the question, how is VI a linear combination of the columns of the matrix inverse? Right, so it answers this question. And indeed, because VI is one of those vectors, that answer is going to be 0 times most of the vectors plus 1 times whatever VI is. And so this tells us that the matrix inverse times V is just going to be a whole bunch of zeros with 1, 1, wherever I is. This is the ith entry. That's what this inverse times the vector is going to be. Right. In some sense, this is a change of basis. You're changing from the standard basis to the other basis. And now we're going to multiply this by this diagonal matrix times S. So now we're going to go to the next one. Here, we're just stretching every component by a factor of lambda I. So it's going to be a different factor for each one. But in particular, the ith entry is going to get stretched by lambda I. So now we're going to have, instead of a bunch of zeros and ones, we're going to have a bunch of zeros and lambda I, where this is also now the ith entry. And we're going to multiply that by S. And now finally here, we can evaluate this. Now, if you do matrix multiplication with rows and columns, this may seem a little awkward, but if you do it out, this right here is just going to give us precisely lambda I times the ith column, which happens to be lambda I times VI. And so now we're done with this direction. We've shown that, in fact, if we started with VI and did SDS inverse, that actually gives us lambda I times VI. And since that's what we get for A, they coincide on a basis. And since every matrix is uniquely defined by how it transforms a basis, this says the SDS inverse is actually A. All right, so far, what have we done? We've shown that if you have a bunch of eigenvectors, then you can diagonalize the matrix. Right? You can use those eigenvectors and eigenvalues to diagonalize the matrix. But now what we want to do is we want to go backwards. So what we're going to do is we're going to suppose that A is equal to SDS inverse, and our goal our top level goal is to show that A has n independent eigenvectors, right? But what our real goal is going to be is to show that the columns of S are eigenvectors. If we show the columns of S are eigenvectors, then since S is invertible, they necessarily have to be independent, and then we're done. And this follows in almost exactly the same way that we did before. We can go back and just almost copy and paste what we did before. So we can just take this evaluation. And the main difference here is that we don't actually know that these are eigenvalues. The only thing we know about this diagonal matrix is the fact that it has diagonal entries. But we can apply the same idea and we can evaluate the same way. We know that this first part here, V times the inverse of S, well, this is just asking again how to create VI as a combination of the columns of V. Well, that's just taking a single vector of VI and 0 of everything else. And then we're going to multiply by the next one. And this next one right here just says stretch each, that diagonal matrix just says stretch each component in the vector by exactly that amount. Well, there's only one non-zero entry here. So it's going to stretch that one by whatever DI happens to be. And then finally, this last one, just like before, is going to give us whatever the ith column is. That's all we're going to be left with. And so we're left with D times what we started with, or DI times what we started with. So it's an eigenvector. And that means we're done, right? We've shown that the columns of S necessarily are eigenvectors, which is exactly what diagonalizability does. All right, so why do we care? So the main reason why we care is that we can compute large powers of a matrix. So for example, a to the k just means a times a times a k times. But if we suppose that A is diagonalizable, and keep in mind that not every matrix is diagonalizable, but if it is diagonalizable, and it turns out that almost all matrices are diagonalizable in some way of diagonalizability, then we can write this instead of A times itself K times, we can do S D S inverse times itself K times. And now the beauty here is these middle S's and S inverses are going to cancel. And so the only thing we're going to be left with is we have these D's in the middle. We're going to have K of those D's. And we also have one S at the beginning and one S inverse on the backside. And what's even cooler is that for a diagonal matrix, when you raise a diagonal matrix to a power, this is just raising those diagonals to that power. So now instead of multiplying K matrices to take a large power of A, you actually only need 3 matrices once you find the eigenvectors and eigenvalues. It makes it much easier to find and interpret what the powers of the matrix are and what they do. So this also illustrates another fun fact that you've probably seen before, and that is that if lambda is an eigenvector or an eigenvalue of A, then lambda to the K is an eigenvalue of A to the K. Right? Because keep in mind, this is the diagonalization of the power of A. A to the K is this diagonalization. And so we know that S is now the eigenvectors of that power matrix. And then this means that the diagonals are the corresponding eigenvalues. And what's even cooler about this is that this gives a way of interpreting what a to say the 2.5 or a to the minus 4.5 or a to the pi. Right? It gives an interpretation for non-integral powers of a matrix. It just means find the eigenvectors and find the eigenvalues and raise those eigenvalues to whatever that power is. All right, so that's really one reason why we care. Maybe as just a quick kind of thought, maybe quick curious question. Right, so one thing you can do with this is you can ask the question. I'm not going to answer this here, but you can ask the question, for example, does this matrix right here like in some sense, what's the limit of this matrix as k goes to infinity? Does this go to the zero matrix? Does it go to something else? What does the limit of this matrix look like? And it's not, you can't just apply a simple rule like you did in calculus with just the entries of the matrix. You have to go to the eigenvectors and eigenvalues and then interpret it. So this is kind of like you're going to use this to do this. So that's kind of where we're going with eigenvalues and eigenvectors. We're not going to do that right now, but I at least want to point out this is the type of question you can ask from diagonalizing a matrix. All right, so the last thing I want to talk about today is about examples of non-diagonalizable matrices. And I'm going to put a big asterisk here. So it turns out that most matrices are diagonalizable in some sense. You have to make some exceptions to them. But right now, what we mean is we mean real diagonalizable. That all your entries in all of your matrices for S, A, and S inverse have to be real. So here's one example. So let's see what this matrix does. So we're going to do a quick before and after graph. We're going to take some standard vectors and maybe some other ones. And we're going to ask, okay, what does these do under the transformation 1, minus 1, 1, 1? So we're just going to graph what these do. And so the 1, 0, it's going to go to 1, 1. The 0, 1 is going to go to minus 1, 1. This one right here, minus 1, 1, it's going to go to minus 2, 0. And this one right here, minus 1, minus 1, it's going to go to 0, minus 2. And so we can look for some eigenvalues and eigenvectors by just comparing which ones are going to go in the same direction. And we can see, if we kind of compare, that in all the cases here, all the vectors never align. In fact, they're 45 degrees off, right? So they're 45 degrees off of where they started. So no vector is ever going to be in the same position of where it started. So this is an example that you can't find any eigenvectors, at least not any real eigenvectors, because there's no vector in the same direction of where you started. All right, so that's a nice example that you can see. And here's another one that's kind of nice. This is one that you can actually prove algebraically. You can prove all these algebraically. This is one you're going to prove algebraically. So we're going to take these same vectors here and see what happens. And something different is going to happen here when we do this. So here, when we do the after graph, right? We have this vector right here is the same, right? My 0, 1, 1, 0 does go to 1, 0. And 0, 1 goes to 1, 1. And minus 1, 1 goes to 0, 0, 1. And this vector here is going to be, this is minus 1, minus 1. That's going to go to minus 2, minus 1. And then just for giggles, let's just put the minus 1 over here down. Just going to go right here. And so what you can see what's happening here is that all these vectors are kind of shifting. They're kind of shearing in one direction or another. And the only vector that's actually going to stay put is the one that's precisely on that x-axis. So only the things on that x-axis are the things that are going to stay put. Everything else is kind of, if it's negative, it's shifting to the left. And if it's positive, if it has a positive y value, it's shifting to the right. So nothing else is actually going to have an eigenvector except for 1, 0. And that's only one dimension. So it has one eigenvector, but it's missing a second one to be diagonalizable. So those are examples of non-diagonalizable matrices. And we're going to figure out how to correct at least this first case. So it turns out in this first case, it has non-real eigenvectors and non-real eigenvalues, and we'll learn how to correct that. And there is a way to correct this one and kind of call it diagonalizable, but that's not in the scope of this course.